All right, class. Welcome back to another lesson. We're still in kind of a probability section of our textbook right now, where we'll be using ideas from that fundamental principle of counting and extending them into a real specific type of list called permutations. And permutations are kind of a special way to counter group things. When we're counting, a permutation is a situation where we care about the order of things, um, and where we're out not using things more than once or we're not repeating them. So that's what we'll be studying today in a variety of examples. One thing that I think is important for us to think about before you start this lesson, maybe as a shortcut to that fundamental principle of counting for different situations. So yesterday, we saw that was really good at working with a total number of outcomes by just multiplying the number of possible options for each thing happening. Like flipping a coin, you could get heads or tails. So there were two options for flipping a coin. And then rolling a die would have 6 options. So if we want to know all the different possibilities we could get by flipping a coin and rolling a die, we would do 2 times 6 to get 12. We can use multiplication as we have throughout the year in other ways as well. Like if we want to look at rearranging letters in a word, this is actually taken from our textbook from a lesson we didn't do, but if we look at the word math and we say, hey, how many different ways can we rearrange those letters? Well, in the first position, we could have an M, we could have an A, we could have a T, or an H, so there are 4 options for that first event. The second letter, because we'll have already used one of those letters, is only going to have 3 options. Then that third position only has 2, and the final letter is kind of just determined by what's left over. So really, to get this result list, we just do 4 times 3 times 2 times 1, which you may have seen in a past course, can be called 4 factorial. And you'll see it on your calculator just like that with an exclamation point after the number. That's just a shorthand way to write a number multiplied by each of its descending values in whole number form until you get all the way down to 1. So 4 times 3 times 2 times 1. In this situation, that gives us 24 possible ways to arrange math and look differently. All right, that idea is really important. I think it'll help you be successful in this lesson. Right off the bat, you'll be using something similar in 10-121, except we'll look at what happens if we're not actually using all the letters or all the different possible choices. As you go through, hopefully, you'll see a pattern emerging and be able to develop a formula to be able to work with permutations and to calculate the number of permutations for given situations. Check closely, rely on the answer key I've attached as well because it has some really good information. And then once you're done, come back to this video and we'll go over some of the key ideas. So go ahead, pause the video now. Good luck on the lesson, and I'll see you back in just a little bit. All right, and welcome back. So hopefully this is you returning after doing really well with the lesson. Let's go over just a few of these ideas so you get some of the really important concepts. So if we look at 10-121, we have Jasper who's picking a PIN for his bank account. And they tell him that he can't repeat a digit, but he can use any digit 0 through 9 to create a PIN. So he needs a 4-digit PIN using 0 through 9. So if we think about this with an event chart, so we have 4 different digits, 0 through 9, which is really 10 different possible choices, and he's not allowed to repeat. So we could just start thinking, okay, for that first number he picks, he's got all 10 choices. For the next number he picks, he's down to only 9 different options, then 8, then 7. So we can multiply those out to get the total number of choices that he has In this situation, I believe we end up with 5,040. This looks similar to what I just showed at the beginning of the video, rearranging the word math, in that we're multiplying numbers by one less as we go across. But it's not really 10 factorial because we stop at 7. The coincidence here is that the difference between the 10 options we had and the 4 that we're picking is 6, and that's how many values we excluded after that 7. So instead of doing just plain old 10 factorial, we actually did 10 factorial over 6 factorial. And the reason that works, we could think of it as 10 times 9 times 8 times 7, and we could write out the full factorial. But then in the denominator, we would do 6 factorial. Oh, but let's do it in an order. And we can cancel out all of those. So this gives us the situation. They actually show that in that first problem of our textbook, and believe it or not, that's kind of giving us the equation to calculate permutations that you really were using and developing throughout the entire lesson. That equation ends up being represented as a permutation with n different possible things to choose from and r different events or things that you want to choose. So that permutation is equal to all of the possibilities to pick from over the difference between all the possibilities you want and how many spots you actually have, and we take the factorial of each. That's exactly what we did when we did this first problem. We did 10 factorial because there were 10 different numbers divided by the difference factorial between the number of choices and the total number of options we wanted for our pin, or the total number of positions for a number in our pin. So this is the equation for permutations right here. And that actually is what you were using in some way or another throughout the entire lesson. If we look back at some of the other problems, we can look at 122, which had situations that had permutations. Part E was technically not a permutation because they allowed repetition, but all of the others were permutations that could use that equation given, or that method, even if you didn't know the equation at the time. So for example, when you have 52 contestants enter a contest for a new school design or logo design, and how many ways can judges pick the best logo and the runners up 1, 2, and 3? Well, first off, just to be clear, when they say runners up 1, 2, and 3, the first runner-up is actually second place. The second runner-up is third. The third runner-up is fourth. So there's actually 4 different places you could be in this competition. So we could do 52 factorial divided by, well, 52 minus 4 is 48. So 48 factorial. And if you do 52 factorial over 48 factorial, you'll end up getting 6,497,400 different possible outcomes, which is a lot. So a lot of different ways that they could pick those results if we're thinking about them as permutations. If we jump down to part C of this problem, they're looking at lockers and combinations. But the funny thing here is in math, a combination is actually slightly different from a permutation. So really these should be called locker permutations if we're thinking about them mathematically. So on that locker, we can pick numbers 0 through 35, and let's do that one quickly. So if we have 3 different numbers, 1, 2, 3, and we can pick numbers 0 through 35, that's actually 36 different options. So we could do, well, 36 times 35 times 34. And that honestly is really a way that makes sense to me, and I'll bet it does to you as well. But using a formula might be helpful in some other situations. So if we think about that NPR is equal to n factorial over n minus r factorial. We can fill in that we have 36 different numbers we could pick from, but we only really want 3, and then all of a sudden it becomes 36 factorial over 36 minus 3 factorial, and that just simplifies to 36 factorial over 33 factorial. So there's another way you can approach this problem. When you get to part D, where they say that all of a sudden Carmen is only allowed to use 0 for the second or third numbers, then we have to think about this a little bit differently. We can't technically use the equation, but we can think about how we can just write the event chart again. So if we're limited on when we can use 0, well, that means there's only 35 options for that first, because you couldn't use 0 there. But then in the second position, you can use 0, but you'll have taken one number already, so there's still 35. And then finally, because 2 numbers will have been removed from the list, you're down to 34. So that would be how you could calculate the outcomes there. And that answer ends up being 41,650 different choices. So those were all permutations. And then jumping down to 123, we're just given some different looks at it. They actually list out the different permutations of A, B, and C, where order does matter there. And they make the point that that's different than if you had like magnet letters A, B, and C that you were rearranging, because you can repeat in this first situation. And so with that repetition, it's technically not a permutation. However, on the fridge, moving those magnets is a permutation because there's no chance of repeating there. So that's something just to be clear. And even occasionally I find myself calling something with repetition a permutation, but it is not by definition a permutation there. So that's not what your permutation equation will work for. As you go through, most were pretty straightforward, especially now that I've shown that formula if you didn't have it already. However, in 125 with anagrams, they introduced the idea of words that had the same letter in them once or twice. For example, B has the word sash, and sash has the letter S in it 2 times. So this one, it's kind of tricky because technically, well, you're not repeating S, but that letter being there twice changes things a little bit. Whereas mash could be calculated. Let's write this out. So mash, we could use that idea at the beginning of the lesson. Well, we have 4 times 3 times 2 times 1 different options here. That ends up giving us 24 possible ways to arrange those letters. Sash is a little bit different. They recommend using a tree diagram because really S showing up twice means that some different things can happen. This is almost like S sub 1 and S sub 2, but they don't look any different if you flip them. So it's like, well, yeah, technically they're in different positions in that original word, but switching S1 and S2 doesn't give us a different result. So really what that does is it effectively cuts our number of outcomes in half. And we're only given 12 as we work through this because every flip of S1 and S2 is just a repeat of something that had already happened. So it really doesn't change things at all. That is something that always happens where to calculate with repeated letters, we'll take the actual number of permutations divided by the factorial of the number of repetitions. 2 factorial is just 2, so that's why that worked out. When you were given that third option that had 3 repeated letters, which was SAS, really moving all those S's around and replacing one another with them doesn't change many things. Ultimately, the only way we can get different looking things is to move the A from the first to second to third to fourth position. So there's really only 4 outcomes, and you can get that by getting your 24 and then dividing by, we have 3 repeats, so 3 factorial. 3 factorial is 6, 24 divided by 6 is 4. So that's a shortcut you can use, is to calculate what would be the number of permutations if there were no repeats, and then divide by the factorial of the actual number of repeated letters. So that was kind of an interesting situation there that I wanted to make sure we saw. If you still have questions after looking at this video and relying on the answer key, please let me know and I'll get you answers to those right away. This is kind of leading into just one final topic on probability before we transition back to circles for the rest of the year. All right, guys, have a great day.